imagine my excitement to know there was a special guest, and then my disappointment to find out it was me. You know. This will be short, and the advantage I have, I guess, is that I'm not a geochemist, and I know almost nothing about geochemistry, so I was able to think of other possible schemes for differentiation of continental crust. And basically, the principal means used by igneous petrologists to argue for differentiation of the continental crust is gravitationally unstable material dripping off the bottom of arcs. And in looking at xenolith suites and in looking at some ultra-high pressure terrains, I've noticed that a lot of them were actually quite felsic, but still had physical properties, basically densities and velocities, that made them look like lower crust. And so I thought about, is it possible that the lower continental crust is actually mostly upper crustal material that's gotten stuffed into the lower crust, rather than being some kind of more refractory material instead. So one can envisage a range of different tectonic scenarios in which upper crustal material gets stuffed in the lower crust, and that includes subduction of continental margins, where the continental margin doesn't make it back to the surface of the Earth, but in fact remains stuffed in the crust. What's this one here? Subduction erosion, so any material that's removed by ablation from a subduction zone, and this is ongoing in about half the arcs today. That material doesn't have to go to Hades, as Dave Scholl and Rolly Van Huene surmised, but in fact could be underplated to the base of the crust. And subducted sediment could do the same sort of thing. And then finally, when an arc is subducted, I don't see any reason why the felsic part of that arc couldn't potentially delaminate from the mafic part and end up at the base of the upper plate. And in each of these cases, the temperatures these materials reached, demonstrably in the case of actual rocks, were quite hot. And so the potential for internal either chemical or density differentiation exists. I don't know what your next slide is.
It's your column with the heat generation.
Ah, yeah, okay. So to push this idea...
You might just point out that you actually, what informed this was calculations of, you take various kinds of sediment and you put them in a hot, high-pressure environment. Some of them want to sink, and up to half of it actually wants to not sink.
Yeah, so the point that Mark is making, which is driven home most beautifully by a suite of xenoliths from the Pamir, is that in the Pamir, the xenolith suite consists solely of crustal rocks, and they range in composition from good old dirt to basalt, and they achieved temperatures of about, well, in excess of 1,000 degrees centigrade during subduction to depths of about 90 kilometers. And at those conditions, basically all the rocks, as emphasized by, say, Max Schmidt and Jörg Hermann in experiments, change to a relatively dense and refractory material as a result of melting and devolatilization. And this provides a mechanism by which relatively dense material, that is dense with respect to continental crust, can be produced, and also a more buoyant differentiate can be produced as well.
Brad, if you go back to the previous slide.
Yes, sir.
You have lots of beautiful colors there. Seismologists can make images with common colors too.
Yeah.
There should be some correspondence to that.
Yes.
So do seismologists provide any evidence for any of those four options?
In my view, most of the work to be done in answering that involves looking at anisotropy. And not being a seismologist, but talking to quite a few of them, my understanding is we're not there yet. Is that a fair statement, Doug?
Yeah, I think so.
I mean, we're still arguing about why, for example, there are low isotropic VP-VS ratios, let alone anisotropy in the mantle wedge in some places. And there's a host of possibilities for just that, including the suggestion that it's quartz, which would be entirely compatible with this, although I find that suggestion implausible for other reasons. Yeah.
Would perhaps prefer terrains be some kind of evidence for a remote relamination process?
Yes, probably the best example of ultra-high pressure rocks that would fall in this category are from Chaidam in central China. And Mark's colleague, Onion, showed that these rocks arrived at the base of the crust. I forget exactly the time scale, but something like tens to hundreds of millions of years before they were finally exhumed to the surface. More? So to push this idea to its extreme, and I'll say right up front, it is pushing it to its extreme, what can one say about the composition of the lower crust, given what we know? So we know seismic velocities, and it's been demonstrated most elegantly by Mark Bain and Peter Kellerman that seismic velocities are not a particularly good proxy for composition. And we also have heat flow measurements from out of the surface of the Earth of something like 50 milliwatts per cubic per square meter. And then there's some estimates of what the mantle heat flow is, and those range, as far as I know, from something like 11 to 17 milliwatts per square meter. And so this is Roberta Rudnick and Shengao's most recent model for the composition of the crust. And they basically took what everybody agrees is the composition of the upper crust, because we can see it, and they took velocities and this assumed value for mantle heat flow and then the known value for surface heat flow, and from that divided the crust into 3 layers and inferred what the compositions of those layers were. And basically, Peter Kellerman and I made a similar kind of approach in which we took the same heat flow at the top and the lower bound on heat flow at the bottom and are able to derive a much less mafic lower crust. I think this comes from Jopar and Marichal and another paper that came out about the same time, whose authors I forget. Pardon me? No, I think the paper I'm referring to had a range of numbers that they thought were viable, and I simply picked the lowest one to as I say, make the most extreme case. Yeah. Yes?
I seem to recall that when Roberta was debating with Teller and Continental lower crustal compositions, there were some bounds that were argued about that had to do with if you put too much heat production in the lower crust, you got too much potassium uranium in the lower crust. You can't maintain a geotherm such that you end up with sort of a solid lower crust. Are you within that bound on the right-hand side? Do you know?
Our temperature here must be hotter because we have a lower basal heat flow. I don't actually know how much hotter. Didn't do that.
I'd be interested to look at your seismic velocities. It seems like that's a lot.
Yeah, it turns out that, I mean, one of the things that got me... That's right. And one of the things that got me started on this was a suite of xenoliths from central Tibet that come from the lower crust. And if you calculate the velocities of those, which have a lot of garnet and kyanite and other fast minerals, they look like basalt. And, yeah, that sort of got me thinking, And then I noticed a number of other people had come to the same conclusion, that seismic velocity as an isotropic parameter by itself is not such a good proxy for composition, unless it gets beyond a certain value, in which case it's, I would say high sevens. Then it's hard to argue. Yep. Yes, sir.
Very interesting as, I think, perhaps significant implications for the crustal geothermal flux. Do you have estimates of the concentrations of uranium and thorium perhaps?
This probably bounds the uncertainties, I would say.
For your model, though, that yours can't be there. 10%.
Again, let me say I'm not a global or bulk system geochemist. I can't say that. I can't give any sort of a sensible answer to that. You have to talk to these guys who know that sort of thing.
Okay, move on. Okay, thanks, Brett.
Yeah.
Excellent.
Okay, actually, well, just a couple of things. You saw this slide or variants of it last week. We'll just quickly cover it, that there is, in fact, if you ask the continents how old they think they are, at least the surface exposures, there, in terms of Sumerian model ages, there's, clearly, 1, 2, 3, 4, 5 peaks here. This is from Bennett and McCulloch, and in fact, here's Armstrong, Taylor, McLennan, and so on, shown here in a linear curve. And what's interesting about this is that, in fact, it matches, as you'll see in the next slide, the Detrital Zircon record. So those don't necessarily have to coincide. This is probably the best measure of when the rocks exposed at the Earth's surface today, in fact, were extracted from a juvenile source and sequestered into the continents. Whereas the zircons have ways that they can dissolve and reprecipitate, and they're giving information more directly about the timing of orogeny rather than transfer of material from the mantle to the crust. But if this is a growth record, one question to ask is, if you look at heat generation as a function of age province, it decreases systematically from Phanerozoic to Proterozoic to Archean. So what is it about, corrected for decay of radioactive heat generation, so what is it about the present exposure that is, in fact, why is it different from the Proterozoic, and why is it different from the Phanerozoic and modern mobile belts? So it was argued for some time that that this observation suggests that the material that gets preserved from early in Earth history, in fact, it was preserved because it was freakishly low in heat generation. A dry, non-radioactive piece of charnicite, is less likely, in fact, to invite a rift to form and then expose that rock to the Wilson cycle. So I think we want to be careful about looking at the preservation record at the Earth's surface, because, again, I emphasize we have actually investigated 0.0000001% of the Earth's crust, which is not immediately accessible to us. And so, raising the question, is our sampling distribution adequate? In fact, this particular distribution is from Australia, North America, and Fennoscandinavia. Here's a zircon record. You saw this last week at Jeroen's talk. And again, here's 1, 2, 3, 4, 5 peaks that they think relate to supercontinent agglomeration, and a number of other peaks that could reflect subduction systems. But there's no question that, and as Condi emphasizes, if you look at the distribution of detrital zircon, they did a number of studies from 1998, just when this method was taking off, and more recently, it's pretty robust. So it's sure, certain portions of Antarctica are remote from our ability to sample, but the present distribution of materials strongly indicate these 5 peaks. Now, here's something Brad sort of alluded to, and that is that back in the 1970s and 60s, it was thought that the continental crust formation was simple. You made an island arc, and you slammed the island arc into a continent, and you grew it in this way. But during the late 70s, early 80s, convergent margin geochemists became dissatisfied with that, and pointing out that if you look at what you think primitive arc magmas are, or if you look at the trend of island arc rocks relative to our finest pundits' estimation of what the bulk continental crust composition is. And I say this is important because, for example, if Brad is correct and it's more felsic than previous estimates, this changes the game. So how do you go from this trend here to this trend down here? And there's a variety of explanations, one of which is we don't know what the composition of the continental crust is exactly. Another is we don't know what the composition of arcs are. Brad mentioned Peter Kellerman. He argues, at least for the Aleutians, that if you look at 2D cross sections through the through the elutions and the adjacent batholith that in fact the average composition of tertiary magmatic rocks is about what a typical estimate of the bulk composition of continental crust are. Primary arc magmas that I showed in those stars, the blue stars in the previous one, are not as high MgO as indicated, that those in fact could be what are called adikites, direct melts from the slab. Another possibility is that in fact the crust was forming in the past by a different mechanism than we see today, that arcs were different in composition. But the most popular view is that there's got to be some way for you to get rid of, the continents, to get rid of this mafic complement, to go from this trend here to this trend down here. Yeah?
Just to add to that list that you just showed, this is one that Roberto would remind us of, erosion.
Yeah. Yes. That in fact you could fractionate the chemistry of the continents by making clays and fractionating the clays to the continental shelf and some components to seawater. But this is a popular view, which is that if this is some primitive material, some juvenile material heading towards the crust, and you have this differentiated crust up here, that there's simply fractional crystallization. Bowen's reaction series takes over, produces a mafic cumulate that becomes unstable and drips off or falls off or is plied off in some way, or interacts with the downgoing slab to be removed. Okay. I think in some respect, Rick, you're going to come and sort of address this from a different perspective. But what's, if you were to psychoanalyze geochemists, at least part of the diagnosis would come back schizophrenia, because on one hand, this is a very popular way to get rid of this seeming mafic complement. Okay, to explain why the continents are more felsic than arcs, but on the other hand, it's going to wreak havoc with the mantle lithosphere, in which you've already heard, appears to have great antiquity. So if you have, for example, multiple Wilson cycles, multiple orogenic events, the likelihood of this mechanism occurring and retaining the ancient mantle lithosphere it's hard to envision. Okay, and I thank John Davidson for those slides. Okay, a couple of assumptions here. I'm going to turn it over to Rick shortly, but I would say that it's fair to characterize the paradigm for the last 30 years or so as viewing that the crust is vertically stratified. You saw the slide Brad showed of a 3-layer crust with a relatively low silica lower crust. That's a pretty popular view. And again, as Brad said, and I'll just in fact show this slide from Rudnick and Fountain, that if you look at igneous rocks versus metapelites, that in fact up to about 7.2, 7.3, garnet-bearing rocks in fact have similar densities and P-wave velocities as equivalent mafic rocks. As you go to ultramafic, then there's just no question. There is no aluminum-rich complement to that. So, but as I said, I think there's a growing sense that seismic velocity is not a good proxy for composition. Here's a widespread view that, in fact, goes back 100 years when, the story that Kelvin realized, or was aware that he may be incorrect in estimating the age of the Earth because of heat generation. And Rutherford caused him to wake up during his snooze in a famous address in London about 105 years ago. That it became clear that radioactive heating, in fact, could keep the Earth hot for much longer. And of course, that introductory textbook view is oversimplified because, in fact, if you could tell Kelvin our present estimates of uranium, thorium, and potassium in the crust, you could go away in a corner, do a calculation, come back and say the Earth is still 100 million years old, because this is not about radioactivity. It is about the ability to exploit heat deep in the Earth to the surface by a mechanism other than conduction. But what's fascinating is if you look at the history of heat generation measurements, they were wildly overestimating the heat productivity in the uranium series. So if it seemed at the time that this immediately caused the paradigm to shift to, the Earth can be old, it was in fact because people were really screwing the measurements up badly. And the heat generations were such that when Holmes did his global thermal model, he had to put all the planet's radioactivity into this, tens of kilometer thick layer at the top because, Strutt's measurements, for example, were incorrect by a large amount. So if the community came over immediately, it was in fact on a false premise. But this idea of an exponentially declining heat production really stuck around and was sort of made popular again in the 1960s. But the problem is fourfold, I guess, that in fact the geophysical basis in which this mechanisms reactivated is the idea that there's correlations between heat flow and heat generation. And Kevin Furlong and his colleagues showed some time ago what appears to be the case in a one-dimensional planet is actually more complicated in a 2D planet because heat doesn't just flow towards the Earth's surface, it flows laterally. And that if you look at a crust with a heterogeneous distribution of heat production, that in fact at the surface, as a result of lateral heat flow, you'll see misleading representations of what the scale length of the radioactive layer is, and misestimate the basal heat flux as well. From my point of view, there is no mechanism whereby the crust can take heat production in the lower crust and move it to the upper crust. Okay? There's ways that the upper crust can retain, by passing an oxidation reduction boundary. Uranium can be enriched in the upper crust. But most of the uranium and thorium in the Earth's crust, the vast majority, is contained in accessory minerals. And we've known for 30 years now that the solubility of these phases in crustal melts is small, almost vanishingly small. In fact, in natural examples, you can go to the Himalaya and you can see the leucogranites that have 40 parts per million zirconium in them, for example, zircon, whereas the source rocks that are right there have 200. Okay? Well, the uranium and thorium are in fact going to go in direct complement to the accessory mineral dominated by zircon. So, what is the mechanism whereby we could even create this exponential distribution? There's proposed candidates, but as yet untested. The other is, in fact, if you look at rocks from the very deep Earth, as in fact Roberta Rudnick did in this classic work here, they're not depleted in heat production. Say no more. So here's sort of the global thorium-uranium ratio of about 4 here. They tend to sort of be plotting to higher values, probably as a result of uranium loss close to the Earth's surface. And lastly, I point out here that if you look at estimates of heat generation in the lower crust, the variance is about a factor of 2. So I'm fond of saying that the argument about the composition of the light element of the core, the composition about the core, the variance is much lower than discussions or controversy about what the composition of the lower crust is. So the lower crust is it's tantalizing, it's right there, but actually there's less disagreement about the composition of the outer core than the lower crust. And lastly, this is generally, I think, a good characterization of a broad part of the community too, and that is that orogeny is not thought to be important to the ultimate crustal architecture. Okay, and I want to just talk a bit about that here. There's an equally distinguished discipline in earth sciences, tectonics, relative to geochemistry. If you look at a large number of tectonic models, here's accumulation over about the last 100 years, you'll notice that if you draw arrows of mass flux, they're essentially horizontal or subhorizontal. Okay? Tectonic models are about taking material from the Earth's surface and putting it down deep, or in some cases, taking it deep and putting it up here along subhorizontal trajectories. Yeah, I better get off. But this is essentially my last blurb. So, can we use tectonic models? As I showed you very briefly, if you ask the tectonics community, is there a mechanism whereby you could take a homogeneous crust and stratify it with respect to silica, or preserve a crust that formed stratified with respect to heat generation silica? The response would be no. Orogeny basically takes rocks and it chops it up and it makes complex mixtures, and there's no obvious mechanism that could return that chopped up sequence to a stratified state in terms of silica, because the lower crust of the crust is the sphere of the Earth most out of thermodynamic equilibrium. Okay, and this is my last slide, and we're going to come back to this right at the end. Why are such disparate continental growth rates? But I'm going to turn it over to Rick.
So what we've seen is that in these various continental growth models, one of the major issues is, first off, the mechanism of crust formation, and also the mechanism that you can destroy crust and recycle it. Both of these always tend to move back towards the question of plate subduction. This is a great way both to make crust at least similar to the kind of continental crust that we have today, and also to get rid of it. Now, there are other mechanisms. There's the IO mechanisms for creating crust. There's Rayleigh-Taylor instabilities for making big drips on continents and pulling them down. But the debate usually ends up coming back to whether plate tectonics is responsible. So I'd like to end up the talk today just by going through some of the evidence that suggests that plate tectonics has been active on the Earth pretty much for all of Earth history. So this one we saw in Jeroen's talk last week. This is a summary from Bob Stern's very nice review paper on when did plate tectonics start. It lists a number of observables that people have used to define when plate subduction are occurring. The point that I'd like to jump on from here, and Jeroen talked about a lot of these things, I'll concentrate on the ones in red here, because these down here mostly depend on the preservation in the rock record of what are in essence low temperature phenomena. So blueschist, ophiolites, lawsonite, eclogites, these are things that plot down in these gradients, which are very distinctive of subduction zones. We're talking about temperatures of a couple hundred degrees down in here. And the problem with this is you go back in Earth history, you both have a hotter mantle, but you're dealing with rocks that have had a very complicated history. And in terms of complicated history, here's a good example of it. This is the Nouveau-Agatek province again in northern Quebec. What you see here are black rocks, which are basically metabasalts that we interpret as being 4.4 billion years in age. These little white strung out veins here are granitic injections that are 3.8 billion years old, and these big white blocks here are a 2.6 billion year old pegmatite that was injected. You see all of these have been torn apart by the activity that this belt has been subjected to. This one, I couldn't resist one. I love this photo. So this is within the mafic rocks themselves. So you see here there's layers that go around this. I don't know if you can see my hammer here for scale. So it goes around like this, comes back here, takes another bend back here, comes here, goes through a quick fold here, and then goes down this way. These folds are delineated by concentrations of garnet in these rocks, and we know that these garnets are forming at about 2.5, 2.6 billion years ago, and they're forming at temperatures of about 650 degrees. So if this rock unit formed 4.4 billion years ago, its current structure is being determined by tectonic processes operating at 2.5 billion years that have nothing to do with the mechanism of formation of these rocks. So you have to be careful when you're using these sort of low temperature indicators of subduction. The stuff down at this side in terms of interpreting whether or not these old rock provinces actually formed in a subduction setting. There are other indicators that are less sensitive, not immune to this, but less sensitive to these orogenic events happening later in Earth history. Arc igneous rocks, and then direct isotopic and chemical evidence for subduction. So let's look at the chemical evidence. Here's another one of these normalized incompatible plots that I'm sure you've all grown to hate by now. You've seen a lot of these. On these diagrams, I tried to show you last week that if you look at both ocean island basalts and ocean ridge basalts, most of the patterns tend to be fairly smooth on these diagrams. When you move over to subduction zones, however, you start getting these very spiky patterns, and you get them for reasons that we know pretty well. So you look at this, here's a dacite from the Andes. What you see is it's a very steep pattern here. It's got a big spike, positive spike in lead abundance, and a big drop in niobium abundance, and yet a big excess in uranium. So what we know that happens in the melting of a wet basalt is that you stabilize phases that keep elements like niobium and titanium, which isn't on here, back. These are phases like rutile, titanium oxide, ilmenite, iron titanium oxide. So these get stabilized during the melting conditions that produce these melts, or
not necessarily melting, but fluid.
Not necessarily melting. It's either melting or fluid release. I would say in the Archean it probably is melting, but in any case, you create these anomalies. So Mark was showing a lot of plots of niobium and uranium. The reason that that is used is because you get these big negative spikes in niobium. These are symptomatic of subduction zone systems, and you get these big enrichments in uranium because uranium is soluble in the fluids, so either fluids or melts that are coming off the subducting slab. So you end up with melts that, here's an example of a continental arc, so these very enriched, very spiky patterns. Here's a very primitive arc lava from an ocean basin. This is the Marianas arc, so there's no continent involved in here, so you can't argue about the amounts of continental contamination here. But you see the same sort of features, so big positive spikes in lead, big negative spikes in niobium relative to uranium, for example. And then I threw in one very unusual lava type. It's called a bonanite because I want to use it to make a point later. Bonanites are unique to arc settings. They often occur in 4 arcs. They show this odd depletion in the middle rare earth elements in here relative to the heavy rare earth elements. About the only way that you can get this is actually to have these rocks derived from a source that had been melted previously. So these are a second stage, or a melt derived from a second stage source, where the incompatible pattern in that source probably once looked like that. So it would be terribly deficient in these elements. But you've added those elements back because of these subduction-related fluids. So you have this evidence of a refractory source is indicated by that slope that under normal circumstances would not remelt simply because it's too refractory to remelt. But you made it able to remelt by adding back these fluids, which of course are going to include water and bring these funny spiky trace element patterns in.
Before you go on, Mark just told us that there's no mechanism to upwardly concentrate uranium and thorium.
Within the crust.
Within the crust, but dacites are rough at the surface, right? And they're enriched in uranium and thorium.
They are, but basalt.
For every dacite that rubs at the surface, an andesite crystallizes a granodiorite.
Yeah, I mean, Mark was talking about really segregation within secondary segregation within the continental crust. I mean, you can bring uranium to the surface, but you also erupt basalts, which are going to have low. The process of arc formation, though, does transfer elements like uranium, thorium, and potassium into the continental crust. So that's one of the mechanisms that you can generate the peculiar composition of the continental crust that you would not do in normal ocean ridge or mid-plate settings. Alrighty. So here, this is a very simplified diagram of the TTG suite. And here's another one of the great geochemistry acronyms. This actually comes from geology. TTG-Tonalite, Trondhjemite, Granodiorite. These are basically the white rocks that you find in Archean terrains. They're granites, you would call them. These are rock names, but they're basically high silica rocks. The granitoid rocks of the continental crust. They range all over in trace element patterns, so I was showing you a simple one, but they show these characteristic features of depletions in niobium, depletions in titanium, and as I said, the most common place that you see these in the modern world anyway are arcs. The reason that this hasn't been accepted as unequivocal evidence of arc formation for these old rocks is simply that you can get these in other settings. You can get these anytime you melt a wet basalt. So if you're thinking of a large oceanic plateau that's made out of basalt and you somehow make the bottom of it wet and you raise the temperature of that, the kind of melts are going to come off are going to look like this. Rhyolites in Iceland have patterns, that, at least some of them, that look like this. So you don't necessarily need subduction to get this pattern, but this is the typical pattern that you do see in subduction.
And where are you going to get the water if not?
Yeah, like an oceanic plateau setting, you can only get it wet once. So after you melt the lower crust and bring a rock like this to the surface, the lower crust is going to be dry unless you can get water back to it. What's a good way to get water back to the lower crust or upper mantle? Subduction. All right. So that's the granitoid component of it. The reason I wanted to show you this is a very complicated diagram. Here's actually the map of Nouveau-Architect. So here's Hudson's Bay, and it's right there on Hudson's Bay. So these are basically a group of basaltic rocks with silica contents are in the sort of 52% silica. So they're pretty typical basaltic rocks. They have patterns of all these elements so that range from fairly flat. So you could imagine that these are in, like maybe an ocean ridge setting or something. But then they have another group, two different compositional groups that show on this example, for example, very big depletions in titanium, very big depletions in niobium in here. So a typical Archean pattern, very strong enrichments in the lightest rare earths. And on this group in particular, you see this sort of positive slope between the middle rare earths and the heavy rare earths. So this is the thing that I showed you from the bonanites. This is a very unusual pattern in modern rocks, and you can see it actually repeated here, along again with these very strong depletions in niobium, but the strong enrichments in thorium. So one can explain the pattern that I showed you in the last diagram for the granitoid rocks by wet melting of basalt. So you don't necessarily need subduction to get those. But these rocks are mafic rocks that were in equilibrium with mantle peridotite. And the easiest way that you can get lots of water and lots of fluids with these characters into mantle peridotite is through subduction, where you're taking crustal fluids below a section of mantle peridotite and adding trace element patterns that contain these various funny wiggles, and then remelting that to make these kind of lavas. So, I mean, basically, it's a non-astonishing way to make both the mafic and the granitoid component of continental crust via subduction. So that's the chemical arguments. The other way that you can argue for subduction in old rocks is simply to find crustal materials at depth. The last couple of slides I'm going to show here all have to do with minerals that are found as inclusions in diamond. So the beauty of this is that diamond's only stable in the upper mantle below depths of, say, 150, 140 kilometers, so it depends on the temperature profile. So these crustal materials had to have been subducted at least to 150 kilometers and probably deeper. How do we know they're crustal materials? So one way that is pretty unequivocal, here's a sulfur isotope diagram. This is the 34-32 ratio. This is a measure of how the sulfur is mass fractionated relative to the expectation of simple linear mass fractionation. During chemical processes that occur in the Earth, you only get linear mass fractionation. So this big delta 33 will be 0. So it'll be along this green line. And if you look at post-Archean sediments here, you see there's not a lot of variation about that line. So those green diamonds. There is one way that you can cause nonlinear mass-dependent fractionation in sulfur, and that's to have UV irradiation of SO2 as a gas in the upper atmosphere by ultraviolet light. That's what you see here in the post-Archean sediments, the blue triangles, the Archean sediments. You see this big range in delta 33. So the only way that we know that we can get this type of variation in sulfur is that this sulfur was at one time SO2 in the atmosphere. The change between the Archean sediments and the post-Archean sediments is due to the rise of oxygen in the atmosphere. Once you get the rise of oxygen, you get ozone that blocks off the UV, so you shut down this mechanism once you start getting oxygen in the atmosphere. So what we're using here is just a test of this is what Archean SO2 in the atmosphere might have looked like. When we go to diamond inclusion, so these are iron-nickel sulfides within diamonds, you see a range in sulfur isotopic composition like this, extending to values well outside the range that we see in mantle sulfur, if you will. So this is basically sulfur that was in the upper atmosphere being irradiated by ultraviolet light, that was rained down on the Earth somehow, got into a sediment, and got subducted into Earth's mantle down to the point where it was included in a diamond. So this is pretty clear evidence that you can get crustal materials into the mantle. We saw this earlier. I think this was in your own talk. This is work from my colleague Steve Shire and Steve Richardson, where if you look at sulfide inclusions in diamond that are in equilibrium with peridotite, they follow along this nice line which describes the mantle evolution of the rhenium-osmium isotope system. Rhenium-osmium is unique in that rhenium is incompatible during partial melting, but osmium is compatible. So the rhenium-osmium ratio of the mantle stays low even in producing residues, whereas crustal rocks almost invariably have high rhenium-osmium ratios, and rhenium-187 decays to 187 osmium. So crustal materials will be uniquely defined by high osmium isotopic compositions after some time has passed. So if you look at these diamond inclusions, the ones that have compositional characteristics suggestive of being associated with subduction of eclogites have these very high osmium isotopic compositions, again consistent with the subduction of crustal material. The nice part about this diagram versus this diagram is there's very little time constraints on when this surface sulfur got into these. Here you're actually dating these rocks, or dating these diamond inclusions, and you can see that this elevation to radiogenic osmium starts occurring at about 3 billion years ago. And this is what this paper used to suggest that plate subduction probably started about 3 billion years ago. Except we've been talking a lot about preservation, and I would raise a preservation issue as well with these data. So here's some seismic results from our Copval project of a few years ago. We saw this in Barbara's talk yesterday in particular. This is direct P-wave tomography of southern Africa. So this is a cross-section from Cape Town up into Zimbabwe here. And what you see in the blues are the high seismic velocities that are typical of cold, refractory, melt-depleted continental lithospheric mantle. It extends down to depths of at least 200, 250 kilometers in the Copval craton here, and then up in the Zimbabwe craton. It's interrupted a little bit by this area where the Bushveld intrusion came through. Now, the beauty of doing this kind of experiments in South Africa is that there's tons of kimberlite pipes that have erupted all throughout this area, and these bring large samples of mantle xenoliths to the surface. By large, I mean pieces of the mantle that are this big. So there's a lot of material from the mantle that you can use to investigate. We can determine ages of these with the rhenium-osmium system. And you see there's a very good correspondence between the age of the rocks, which is sort of the average age from each kimberlite pipe here in red, are rocks that are less than 2 billion years. This red outline is the outline of the old crustal rocks that define the Archean craton here. Everything within that and within the blue areas of the tomography give these white circles. So these are mean ages for these mantle peridotites that are older than 2.5 billion years. So what you see here is that there's a good correspondence between old mantle under old crust and on the metamorphic belts around the outside that are added about 1 billion years ago, you get much younger mantle. So we're looking at turning the tomography into an actual age spectrum for continental lithospheric mantle. Now we look at that in detail. An interesting aspect of this is the histogram, or this probability density diagram, of the rhenium-osmium model ages for whole rock peridotites from the Copval craton. And you see, even though the Copval has crustal rocks as old as about 3.6 billion years, these peak at about 2.9 billion years in the case of the Copval. If you go to some other cratons, here's the Slave, it's the North Atlantic, you see this peaks at about like 2.7 or so. This peaks in the 2.5 to 3 billion year range. And Barbara, this is what I was mentioning about a two-layered craton here, is you've got this big peak of the old ages. These are all at shallow depth, and these younger age peaks are actually come from deeper in the lithosphere. So these are probably in the uppermost 100 to 120 kilometers, and these are deeper than that. So there is this age separation in the Slave. You don't see it as dramatically in the Copval craton. So the point in showing this is to show that these cratons provide mantle lithosphere stabilization ages of about 2.9 billion years. So, what does this mean? Do we relate this to the onset of subduction, and that basically these are the result of the beginning of subduction? Or if we go back to the previous slide, the fact that the eclogite diamond inclusions are retained and only show evidence of showing up at 3 billion years, is this simply because the media that they're stored in, the continental lithospheric mantle, wasn't present until that time? So if you had thin continental lithospheres prior to 2.9 and you had subduction, could you store an eclogitic diamond in the mantle?
This is preserving the evidence of subduction at continental margins, but you can always have oceanosial subduction.
No, you certainly could, but the question is, would you preserve the evidence of that in a way that we could eventually get it back as a diamond inclusion in a kimberlite? So those diamond inclusions come from these roots. right? And the explosive volcanism is sampling pretty much that whole route. And so the eclogitic inclusions that were in the Shirey and Richardson paper come from that route. If that route's not there and they were part of a subduction zone that kept going, we would not access those materials. That's the whole point of it. All right. So the last slide that I have here is evidence pushes the subduction back a little bit further. This is a rhenium-osmium isochron diagram. I mentioned that on these kind of diagrams, if you get a group of rocks that are the same age, they should define nice lines. So if we look at an expectation of a 3.5 billion year slope, that's that slope here. If we're looking at materials that formed in the mantle, we know the osmium isotopic composition of the mantle at that time, and with different rhenium-osmium ratios, we should find a group of rocks that would lie along that if they're 3.5 billion years old. When we go to the Panda, this is the Panda kimberlite in the slave craton. These again are diamond inclusions. They're sulfide minerals included in diamonds. What we find actually is that most of the diamond inclusions plot up here, scattering up here. They're not a great line. This is actually one of the best lines that's come out of diamond inclusions. These are individual 50 micron sulfides, so these aren't particularly easy analyses. And osmium is present at the part per million level. So what you see here, though, is that they do fall along a 3.5 GA isochron with a pretty big error, but they give this initial osmium value gammas by percent, so it's 6% higher than we would expect for the mantle that time. And I mentioned to you that the crustal rocks are the ones that generate radiogenic osmium, so high 187, 188 osmium. So the interpretation of a diagram like this is that these diamond inclusions actually formed at 3.5 billion years ago, but they didn't form from mantle fluids. They formed from fluids that had osmium isotopic compositions more consistent with crustal material. And they're forming at 150 kilometers depth in the mantle. So the idea is that if you had mantle down here and you're got subduction and you're bringing in crustal fluids as part of that subduction, you're mixing between mantle that's here, and in fact we see mantle xenoliths that sort of range between this isochron and the expectation for the mantle. But the diamonds themselves, which are probably a direct precipitate of a subduction fluid, are forming along this line that gives a 3.5 billion year slope and an initial osmium that's consistent with a crustal component. So, there are ways out of this, but I would argue that this kind of evidence is suggesting that crustal subduction down to depths of at least 150 kilometers is occurring at least 3.5 billion years ago, and it may be occurring even 4.4 billion years ago if you believe that that's the age of the Nouveau-Agatek rocks that carry the chemical signatures of subduction. So that's all I wanted to say. I think we're done. Oh, yeah, that's fine.
Would it be fair to say that every time you use the word subduction, I could replace it by an unspecified mechanism that carries stuff down pretty more than, say, 150 kilometers?
You could, but the issue here is that it's carrying crustal material down to those depths. With the diamonds, we have it carrying it down to 150 kilometers depth. And, if a Rayleigh-Taylor instability would do that. If you had a big drop at the bottom of a continental lithosphere, it could do that. But these are all the signatures that we expect from subduction. Yeah. We know that it's a physical process that works. We understand the mechanisms whereby it could be preserved in the continental lithosphere. So what this is showing in particular, the continental lithospheric mantle in the slave is probably down here, and you're subducting a crustal fluid that's interacting with material like this to make diamonds that are up here. So in a case like, for example, a Rayleigh-Taylor instability, it would have to be falling through a material and losing bits of its own fluids into a continental lithosphere that's still there so that we can sample it in kimberlites today. So you could create more complicated scenarios, but subduction as we know it today would provide a very simple explanation for this type of data set. This one? This is an area where North Atlantic, a lot of the rocks there are again 2.7. This event at 2GA, I'm not sure. I'm not sure about this data set, so I can't answer that.
If we accept that the diamonds record at least from the beginning of subduction, they also record the oldest preservation of continental lithosphere.
They do.
Preserve those diamonds, you not only have to have the subduction signature, but you have to have a way of keeping them from being lost to the deeper
Right. I mean, this Barbara showed this, and we talked about this earlier. There is this section of the slave craton that's very highly depleted, very low temperature. It's got a 33 milliwatt per kilometer geotherm, or per square meter geotherm, rather than the typical 40 of cratonic lithosphere. It's in the upper 140 kilometers of the mantle. And the reason there's diamonds in it is it's really cold. It's not that it reaches high pressure, it's really cold. So, and this is evidence that it's in fact 3.5 billion years old. So yeah, I mean, continental lithospheric wedges, at least here, are that old.